Welcome back. So we've seen like very different use cases of React on native and TVs. But what about doing data visualization with React? And it turns out that it's possible. So Zach Nation is going to talk about it right now. Zach Nation? Oh, right here.
Hello, everybody. I am really excited to be here. Really excited. This is actually my first conference talk. So I'm Zach Nation. I work at Dato. A month ago, we were called GraphLab. We changed our name to show our focus on broader forms of data than just graphs. So all kinds of data. We love data. And what I mostly do with data is visualize it. So that's what I'm going to talk about today. We love React.js at Dato. This is going to kind of echo the Netflix sentiment. We use it for kind of all the UI that we do. Dynamic web UI is, of course, the normal use case for React.js. But about 8 or 9 months ago, we kind of started investigating how are we going to render visualization. And I want to tell a little short story here, which is that I started out looking at all these visualization tools. I looked at D3. I looked at some lesser-known competitors, some higher-level visualization libraries like Vega. And what I found was ultimately they all kind of do two different things. They talk about how to turn data into what I'm going to call visual elements, which is structuring pixels on the screen, providing sizes and positions and that sort of thing. And then all of them actually also handle rendering. And rendering is just this common theme that all these visualization libraries provide, but it's not really any of their focus. So I thought, let's try it in React. And I built a small prototype, and then it turned out the prototype was so good that we shipped it. So at Dato, we want to enable people to build a predictive application. This is what we're calling basically a data-driven application that provides some predictions based on historical data. And there's a pipeline, a workflow that our API callers will follow in order to build this kind of predictive application. You'll go from understanding the data, picking out relevant information. Data scientists will call this feature engineering, feature selection, building a model, which is mostly a lot of tuning parameters and then evaluating how good your model is. And then when you've got something that you think is good, deploying it to production. And at every stage along the way, visualization is a useful tool here. So we've been building visualization components to support that. Why is visualization useful for this? It turns out human beings are really good at pattern recognition visually. That's just what we're wired for. So this is kind of the really usual example that people trot out for data visualization. Anscombe's quartet. All of the summary statistics for these 4 data sets are identical. Looking at just the numbers, you can't even tell the difference at all. But visually, clearly, they're different data sets. So I'm going to show a real-world example of data visualization. And I'm going to use the Bitcoin blockchain. So for those of you who are not as familiar with Bitcoin, it's a distributed cryptocurrency, and every user of Bitcoin has the entire blockchain on their machine. It's a shared state knowledge of the entire history of Bitcoin. So it's a public ledger. Every transaction is recorded. So I took a copy of this from a few months back. It's 21 gigabytes. And it has a nice property, which is that it's sequentially arranged, so you can visualize it while streaming through the data. And I think visualization might reveal some patterns or interesting information in it. So I started out by parsing the blockchain. And I opened it up in a hex dump. And it kind of doesn't look like much. I can see some ASCII strings in here. But I noticed that there was a little bit of repetition here. F9BE, I saw repeats over and over again. And it turns out F9BE B4D9 is the magic header at the beginning of every block. So this is actually a very simple binary format. And then I wrote it out to a CSV, and I came up with a list of 45 million transactions that have ever taken place. That's it. That's the whole bit. That's all of Bitcoin, 45 million transactions. It's not that many, right? We're doing big data visualization. 45 million is nothing. OK, so let's show a demo. Should we go ahead and switch to my machine? OK, so here I've got GraphLab Canvas. I'm going to do some visual data exploration. This is actually our product. I have a block index, a timestamp, and a transaction amount. So if I want to look at distribution of the transaction amounts, uh-oh, I lost my cache. OK, so it's actually crunching through 45 million transactions now. This is going to take a couple more seconds. OK, so I've got, this is all the transaction amounts that have ever happened in Bitcoin. And it turns out this is not a good histogram because it's getting skewed by outliers. This is a common problem in visualization. If you just take some raw data and dump it into a histogram, everything lines up on the left because you have some outliers. But we can learn something else from this, which is we've used a streaming aggregation technique called a sketch summary here, which gives us frequent items. And so we can see the most frequent item is 0.01. That's the most commonly transacted amount in Bitcoin. Not sure why. 50 is interesting, actually, because it is the amount that was awarded for mining a block for a long time in Bitcoin. So we can see that that comes up pretty highly. One thing I want to show off, so all of this is React rendered, 100% React. I don't think there's a single DOM node here that's not React. All of the visualization components here are SVG. We also use Canvas sometimes, and I'll talk about why you might want to use one or the other. And then a lot of the other information here is just regular DOM nodes. One thing I want to show is actually the data table that we built. So yesterday we saw a data table that can handle tens of thousands of elements. Well, we have 45 million here. And if I want to see transaction number 2, 3, 4, 5, 6, 7, 8, how many? Wait. $3,456,789. I want to see that transaction. And due to a floating point rounding error, we actually got to 790 here. Law of large numbers or something. And I actually want to point out something interesting here, which is that to build this component, I had to hack around the limitations of the browser. Because, so we've got a scrolling table here. And this part I can only reliably fit about 100,000 rows into before the browser itself will give up and stop giving me more scrollable area. And this is a different amount in different browsers. So it doesn't actually seem to be part of any standard. It's just that they've used some 32-bit integer somewhere to keep track of how many pixels tall things can be, and it just really breaks in weird ways in Safari if you don't heed that. So I've actually built this scrollable piece on the left so that you can basically page through 100,000 row pages. And you can get through any size data set this way. We've gone to up to about a terabyte of data. And you can just page through and see every individual row. But that's kind of easy because that's one row at a time. So I want to talk about aggregation. So I built a little demo for this talk, which I'm going to show now. And this is just looking at the total Bitcoin transaction amount per day with some Bitcoin history here. So right now I'm parsing the blockchain. This is actually parsing the blockchain live, that binary format that I showed. That whole 21 gigabyte file is being live parsed right now by node binary on my server with WebSocket sending some aggregated data to this browser about every 2 seconds. And we're up to about March 2010 now, and it's just going to keep going here. And so what you can see is there's some interesting spikes. and they do correspond to real-world events. So here we just saw a beginning of a 10x increase in exchange value over a 5-day period, corresponds to that huge spike right here. So streaming visualization techniques can let you take advantage of a really big data set without paying any upfront cost to analyze that data. You can stream it through and then use those visual pattern recognition capabilities that we all have to start to understand the data in real time. So I'm going to talk about what kind of techniques in React.js can make this possible. Go ahead and switch back to the slides. So what are the challenges in visualizing a large data set like this? We need to condense that data to a smaller set of what I'm calling visual elements. Visual elements is kind of hand-wavy. What I really mean is some kind of a code or an object representation of what's going to get shown on the screen at a higher level than just raw data. And then maintaining a high level of interactivity and performance in the face of crunching through 21 gigabytes of data. That's kind of challenging. And then maintaining interaction state across the whole application UI while controlling a server-side long-running computation that's based on the UI state. So basically, we have to now synchronize that state across two places, which shared mutable state is the root of all evil, I think we just heard yesterday. But that's what we're doing. I think we have to. But it turns out visual elements, interactivity, state, these are all the things React.js is good at. So that's why I originally started looking at React.js as a way to prototype visualization, and that's why we shipped the prototype. So the data visualization pipeline that I just described, to build a visualization component like that, you go from raw data to a rendered visualization through a series of steps. The first step is some kind of aggregation technique. Basically, you have to take that raw data and apply some kind of transformation to it that will shrink it in size very significantly. In this case, for the demo that we just saw, we're shrinking from streaming through 21 gigabytes to a 47 kilobyte payload that comes across every 2 seconds. So something that a browser can actually keep up with easily, and that we can send across the network. Producing a set of visual elements from that aggregated data, which it turns out D3.js, a very popular visualization library, is really good at. That's really, I think, its primary function. And then rendering, which I think React.js is really good at. I've just had great experiences rendering with React.js. Maybe some of you haven't, but hopefully you have. So talking about aggregation, this is basically, again, taking data, crunching it down into something we can send to the browser. One of the principles that you'll want to follow is computing close to the data. You have a super powerful server. Maybe you don't, but imagine you do. You could have the beefiest EC2 machine or a cluster or who knows. And you've got a huge amount of data sitting there on that server or distributed on HDFS or wherever it is. It's too big to fit in your web browser. You're not going to send it all across the pipe to the browser. So you want to keep that computation as close as possible to the data. So to do this, we have an architecture that kind of looks like Flux, but on the server. And this is not what Pete Hunt was talking about at all with server-side Flux. This is totally different. What I really mean by this is that our graph of order of operations looks a lot like Flux, but our components don't all live in the browser. So essentially, we've taken the idea of a dispatcher and replaced it with XMLHttpRequest and WebSocket. This is just communication from the browser to a particular endpoint on the server. And then on that server, we have a stateful server component. This sounds awesome, right? Stateful server. You can just throw all your state there. There's a big caveat to this, which is that it's really hard to do a multi-user stateful server without unbounded memory use and all that. So this caveat, take this all with that caveat, because our product is actually we distribute the server to you and you run it on your machine. So it's a single user server. If you want to do this multi-user, you might need terabytes of RAM. So what do I mean by scalable aggregation? How do we aggregate a data set that might be 21 gigs or even a terabyte in a way that we can send it to the browser in real time? Some of the techniques that we would use for scalable aggregation are binning. If you do this in 1 dimension, you get a histogram. If you do this in 2 dimensions, you get a heat map. And sketch data structures, which power some of the visualizations I showed in our product. I won't go into detail about sketch data structures, but essentially you can do a linear pass over the data, and while you're streaming through the data, you start to get more and more confidence about the summary statistics of that data and the quantiles within the data and all that. So just to give a little visual aid of what binning looks like, that's a simpler technique. Essentially, you're taking groups of data, typically evenly spaced, or you might use a log scale, and then counting or aggregating within each group to produce a total amount. So instead of all those raw data points, you end up with 5 bars of data here. If you are working with scalable aggregation, there are some principles you want to follow. You want to have constant memory complexity, or maybe log n at worst. If you have something like O of n memory complexity, then you might not be able to go through a 21 gigabyte file. Again, unless you have a terabyte of RAM. You want to produce results incrementally in a streaming fashion. This we've found really important to maintain a good user experience while also doing visualization. So a lot of what we want to do visualization on are these huge data sets, but it's really hard to make the user just sit there for 15 minutes and see nothing. We just can't ask users to do that. That's not fair. So we're going to show you the first second and the second second and so on as it visualizes. And by the time you get to the end, you get the thing you would have waited 15 minutes for anyway. So it's really the best of both worlds. And you want to send results to the client periodically. And I use the word periodically very intentionally here. You don't want to send them continuously necessarily, or you will overwhelm rendering to the point where you may be paying a higher cost to render in the browser than you actually need to let the user see what they want to see. So here I was updating about every 2 seconds. I think that's probably a good interval. So here's some code samples. This is actually code from that demo that I just showed. This is on the server side. We're sending over a WebSocket a typed array of the entire aggregated data set. In this case, it comes out to about 47 kilobytes as a typed array. And it comes in over binary. And then on the other side, we actually just do a set state on a React component when we receive a message over that WebSocket. So basically, the entire workflow here is our server component owns the state of the whole application. It knows how far we've gotten, and it's periodically sending updates to the client. And then on the client, we're just re-rendering the whole re-rendering the whole application. This sounded crazy to me 9 months ago, but it turns out it works great. So we call set state on our top-level component, and that chunks up pieces of the data that are relevant to different parts of the visualization and renders. I like to call this isomorphic data structures also. That hist data structure is implemented on both the server and the client with the same JavaScript code. So the next step, once you've aggregated that data and gotten it across, is to turn it into a set of visual elements. What do I mean by visual elements? I'm going to give you a visual aid. This is a real screenshot from GraphLab Create. And here are all of the visual elements that I've identified within it. And what you'll notice is that what I'm talking about by visual elements actually maps really cleanly to React components. Each of these visual elements could be a React component, and that's personally how I would like to structure my code. I think that makes the most sense. You can reason about which things need to cause re-rendering and which other things, and, well, most importantly, you can let React reason about that and just dump data at it, which is what I like to do. So something is interesting about these visual elements that's a little different from most UI rendering you do in React. You'll notice text values are data dependent. That's pretty normal. You take some input as props, and it determines what text you're going to render. Here, the sizes and positions of the elements, and frequently colors and things like that also, are actually data dependent. And this is where D3 really shines in combination with React. So D3, as you all may know, is a visualization library very commonly used. And And these are all the things in D3. It's a huge library. I kind of think this is like the jQuery of visualization. It just has a bunch of stuff. There's a core section, which is very large and includes things like loading things off of the network and CSV parsing and math and scales, and there's things for dealing with SVG paths. But what you really need to know is that about 90% of it by volume are pure functions or small objects that you can call pure methods on that work really well within a React render method. So it turns out, I thought it was actually going to be hard to reconcile all of this code that's out there on the internet to do visualization using D3 with building visualization components in React. It turns out there's only really 3 parts of D3 that conflict with React because both want to own the DOM. One is selections and transitions in D3 core. This is actually really the core of D3. This is what almost every D3 example out there is going to use. D3 selections are how D3 owns the DOM. It has a somewhat different model from React for talking about component lifecycle and how it deals with updating. I find it personally a lot easier to reason about React's rendering, which is what drew me to it. So I'm going to grade those out, and we're not going to use them. And then D3's behavior APIs also are very DOM dependent and probably not easy to integrate with React. The rest of them are great. So use them. They're great. Here's some examples. So I have an axis component. This is a React component that I wrote. And I'm going to pass in a scale property. And this scale property is just a D3 scale object. So I can declare a D3 scale object, give it a domain and range, and let it do what it's best at. At this point, this is now an object with pure methods that I give them data, and they return data. Inside that axis component, I can actually render just directly from D3's data. So really, the 2 libraries work quite well together. So now that I've got a set of visual elements, where am I going to put them to? How do I push pixels to the screen? You have to make a lot of choices about a render target. These have implications. Some of the more common ones are SVG, Canvas, and of course React Art, as was mentioned previously. React Art is a great abstraction layer across SVG, Canvas, and I think it's VML, the weird IE thing. But like any abstraction layer, it doesn't let you get at kind of the interesting differences between the choices underneath. And I actually want to talk about those differences. So I'm going to focus on SVG and Canvas. There's a lot of other interesting render targets out there, potentially WebGL, XAML, Direct2D, now iOS and Android. And I'm not going to talk about those, but you can imagine the same principles would apply. So one thing you have to consider when choosing a render target is the number of visual elements. Some of these render targets are much more efficient at rendering every frame than others. Specifically, Canvas is really, really fast at just re-rendering the whole canvas. You can basically do this every frame if you have a reasonably sized canvas and not too many draw operations. SVG will probably max out way, way sooner, and you can't push as many visual elements to it. Whereas all the other considerations here, or animation and interactivity, have completely different properties across SVG and Canvas. And then browser support, I'm mentioning because that's basically the reason you would want to pull in something like React Art to target VML. So I want to compare SVG and Canvas. If you look at SVG, it has a lot of really nice properties in the browser. I'm talking about inline rendered SVG using React. So React's same tree diffing algorithm applies. SVG DOM elements are just like any other DOM elements, which means you get a lot of great stuff for free. You can use CSS styles. You can use CSS animation and React transition groups and all that. You can use regular DOM events and React events, of course, which is great. And both SVG and Canvas can handle 1,000 or fewer visual elements pretty easily. But there are some corner cases here where you might end up with more than 1,000 visual elements. And the way that might happen is if you want to show something that looks continuous across 2 dimensions. You can go about 800 pixels wide, let's say, in 1 dimension, and you've got 800 visual elements. But if you go 800 pixels by 800 pixels, now you're rendering probably more things than SVG can support with, say, a 2D heat map. So Canvas is really great for those scenarios where you need to render just a lot of different things, pixels with a lot of different values. And you will give up CSS styles and animation and events. Excuse me. So I want to talk about the visualization architecture that we have at Dato. We're calling this GraphLab Canvas. It's 100% React rendered with a stateful server like I've described, using a Flux-like data flow. We use a streaming sketch data structure to perform aggregation while visualizing. And we've tested this with up to about a terabyte of data, and responsiveness and performance remain roughly constant as data size increases. So a terabyte of data in the browser, that's pretty cool. This is kind of an overall view of what that architecture looks like. Essentially, we have on two sides. The one side is the user's machine. We have a web browser running with a React.js top-level component, components underneath, the same kind of component structure you would use for any application, ultimately rendering either to Canvas or SVG, backed by a dispatcher and a store on a stateful server, which can be local or remote. This server could, in this case, it was on my machine, but it could actually be anywhere because we're only sending 40 kilobytes across the wire every 2 seconds. OK, thanks. Questions? OK, thank you.
Thank you, Zach.